All right, everybody, I think I'm gonna go ahead and get started here. Welcome to another week. Gosh, we don't have too many more of those to go. Hope that you guys had a good weekend. Hopefully got a chance to rest a little bit. Are making some progress on that homework that's due tonight. I want to just make a couple announcements before we get into it. Today is going to be kind of a heavy lecture day, just to warn you a little bit. I got to get through this material. So I really want to make sure I get that done. If you have questions on the whole, so first of all, there's homework due tonight. I sat in my office hours a long time yesterday. Didn't see anybody there, but I'm going to be there again tonight, both in person and in Zoom after 5:30. I just take a little dinner break around 6:30, but other than that, I'll be there all the way until 10 o'clock. So I have a lot of office hours today. So if you have questions on the homework that you're turning in for tonight, why don't you hold those for the office hours? We'll do it that way, and I'll do everything. I'll go through everything with you there if you have any questions. There is also going to be an assignment due on Friday, and it's already posted. It will be an assignment that you'll want to do, obviously, before our midterm. So this week we have homework Monday and Friday. My advice will be, of course, to really get started on that homework for Friday early. If you do get it started by Wednesday, I should have time on Wednesday to take some questions on on Friday's homework. So if you get a jump start on anything, it always is a good thing, right? I'd be glad to help you out with that. Our third midterm is next Monday. Let me say a couple of quick words about that. First of all, I sent you an email over the weekend with kind of an overview of what sections is going to cover and kind of what resources to look at online. Don't forget that there's going to be a sample exam that you can try. Probably, I'm thinking more towards next weekend. You try the sample midterm. There's also a video of a review session. You'll find that in Canvas. Totally optional, but I would encourage you to consider watching that. And of course, we've had quite a few group works that we've been doing lately. Lots of stuff to look at for that exam. And I'll probably talk a little more about the exam itself on Wednesday. I haven't even thought about it yet, to be honest with you myself, in terms of what kind of questions I'm going to put there. But certainly, anytime you feel like getting started on your studying, I encourage you to do that. Let's see. Oh, also, you can come to either, if you want to take the test next Monday at noon. I am in the same room at noon. You're welcome to come take it and just get it over with if you want to do that early. Otherwise, of course, the regular class time is fine. I offer both of my classes that same luxury. And so people can do whatever's better for them if they have a choice. I will take one quick moment to jump ahead to 2 weeks from now. 2 weeks from now is actually finals week. Oh my gosh, did I just say that correctly? I think I did. So our finals week is just around the corner. And I had a couple people ask a question. I just want to reiterate this again. Although my two classes on Mondays and Wednesdays are back to back, when it gets to finals week, they get changed like more dramatically. So you guys officially have a final in my class on the Monday of finals week. I think it's from 1 to 3 in the afternoon. If you prefer, you can take the final on Wednesday from 1 to 3, which is when my other class is officially scheduled to take it. It will be almost certainly I will write 2 different finals because it's like 48 hours apart. But I'll only be just curving. It doesn't matter which section you're officially enrolled in. I will just be curving the exams according to the Monday group and the Wednesday group. That's basically how it's going to go. So you can make a choice. You don't have to tell me ahead of time. You can think about it. Some of you maybe don't have a choice. If you have another class that has a final on Wednesday at 1, well, then you have to come on Monday and take it with me here. But otherwise, you have a choice. You can take it on Monday or on Wednesday, whatever works better for your schedule. Yeah, totally up to you. I'll talk more about the final next week after we get through the midterm. I'd like to get that out of the way first, and then we'll talk more about the final. I just wanted, for planning purposes, I just wanted to get that out. kind of get that on your thought process a little bit. Anybody have any logistical questions about anything I've said so far? So this is a busy week. We have homework due today and on Friday. However, I will tell you this, after you get done with this week's homework, there will be one last assignment that only has 2 problems on it and probably takes 30 minutes to finish, which will be next week after the exam. So almost all of the rest of the homework for the whole semester is going to get done in the next 4 days. So that's kind of where we are at. Wow. Yes.
Is there any extra credit offered for exam 3 or the final?
Good question. I have not come up with it yet, but that doesn't mean it won't happen. So I would highly recommend being in class and making sure you don't miss something, because there is certainly a chance that could happen. I normally do like to do something like that. It could be something as simple as just simply being here. Or maybe I will have a video. I think last time I had a video for you to watch. I could come up with something for that as well. So we'll see what I come up with. Okay, but more than likely there will be something. You just have to be on the ball about that. Any other questions? Okay, like I said, guys, I'm just gonna front load this in advance with a quick little, reminder. This is gonna be, there's a lot of stuff to cover today. So try to bear with me. Ask questions though as we go along. I don't want to go too fast. I really want you guys to understand these sections. Everything up through tonight's homework, right? We didn't actually learn yet how to solve our linear system. So here's the linear system of the hour, right? X prime equals AX. That's what we want to solve. I put a little star on that. This is my homogeneous linear system. Now, last week we pointed out that those solutions do form a vector space and that it's n dimensional. The n is coming from the size of the matrix up here. So we know that we can look for a basis. Because if it's a vector space, it's going to have a basis, and we know how many basis vectors to look for. But up through the first 3 sections of chapter 9, nobody has explained how to actually find the basis, right? So when you were doing the homework for tonight, if some of you have already done section 9.3, you notice that they actually gave you the solutions. They gave you the x1 and the x2, and they just said, check it. Check that when you take the derivative, work out what that is, that it's the same as if you take a times whatever that solution is that they gave you. So they basically hand you what's going to work, and they just say, check it. Check that boxed equation and make sure that we really do have a correct solution. But as of tonight's homework, nowhere in there are they actually asking you to solve the differential equation, because we haven't learned how to do it yet. Okay, so we have to learn how to do it. That's what this week is all going to be about. Okay, and it starts in section 9.4. And we did get to this at the end of class on Wednesday, and I got really excited, and then I ran out of time, darn it. So I had to wait 5 days, but here we are. If the matrix is non-defective, we go back to chapter 7, right? What does that mean? Non-defective meant that, let's see, every eigenvalue pulls its weight. In other words, there will be n linearly independent eigenvectors. Here I've tried to just set up some notation, right? V1, V2, V3 with corresponding lambdas. Okay, so we have these eigenpairs. And if we did a good job on chapter 7, then everybody hopefully knows how to find these eigenpairs. And as long as we get n of them, in other words, if the matrix is non-defective, then we can build n linearly independent solutions, which is what is in the box down here, these xi's. And this is just a miracle that this works. If you take e to the lambda t times v, in other words, you take your eigenpair and you use the lambda and the v to build this x of t solution, it turns out that it works. It's a solution to your original linear system. Okay, and you actually get your basis that way. You actually get your basis that way. Just build all of these solutions, And then the general solution is just the span of that basis, right? It's just all of the linear combinations that you can make out of that basis. Isn't that nice? Actually, guys, if you think about it, 90% of what's on the board over here in terms of coming up with the general solution is chapter 7. It's just getting the lambdas and the v's. If you can do that, the rest of it is just going through the motions to writing down the answer. There's never a better way to learn and understand something than by doing an example. So we didn't get to do this on Wednesday last week, so let's do it right now. I'm going to give you an example here. Find the general solution. Yeah, I know. I don't actually need this plugged in right now. Find the general solution to this system. What would you guys suggest? So here it is, x1 prime equals negative 2x1 minus 7x2, and x2 prime is equal to negative x1 plus 4x2. Any suggestions what I should do first? Remember, I want to take advantage of what's in the recap. So what do I not see on the board here that obviously I have to have if I'm going to start working on this problem? Matrix, capital A, right? I don't have the matrix. So I need to start by putting this into a matrix form. So let's just say a matrix formulation. We actually did this last week for sort of a general situation. But remember how the matrix formulation goes? You just put the derivatives of the x's into a column here on the left side. Okay, and then we're going to use a matrix here. This is where we're going to put the capital A in just a moment. And then we're going to multiply that by x1, x2. Okay. Great. So this is a 2 by 2 matrix. How do we get the numbers that go into that matrix? They are just the coefficients from the system. You can see them staring you in the face up here, right? The -2, the -7, and then on the second row, -1 and 4. Make sure that you put those numbers in the matrix correctly. Occasionally, I'll see somebody mix up rows with columns. But if you multiply this out over here, if you do the matrix multiplication, you should be getting these expressions, right, that are on the right-hand side of the system. Okay, great. So this is just your x prime right here equals a times x. That's your homogeneous linear system. So we've got our matrix in our hands. Let's start working on finding the eigenvalue, eigenvector pairs, because that's what's at the heart of section 9.4. So I'm going to do my determinant of a minus lambda I. So I subtract lambda off of the main diagonal of the matrix A. This is just a 2 by 2 determinant. So hopefully by now we all know this one really well, the AD minus BC. So -2 minus lambda times 4 minus lambda, and then -7. And if I multiply that out, of course, I'll get lambda squared minus 2 lambda minus 15. Okay, great. And this actually factors. Let's just go ahead and factor it. It's actually lambda minus 5 times lambda plus 3. So this one is not part of the factor. We're going to set this one to 0 eventually here. Okay, great. So I get my lambda values. My lambda values here are going to be 5 and -3. Notice that there's no repeats, so of course this will be non-defective. Also, it's always a good idea to check those fun facts, right? Go back and review chapter 7, right? If you add up your lambdas, it should agree with the trace of the matrix. -2 plus 4 is 2. These guys add up to 2. The determinant of this matrix is -15. The product of the lambdas is supposed to be the determinant. Okay, so it all seems to be good so far. Next step is that we handle our different lambdas to find the corresponding eigenvectors. So let's take lambda equals 5 here. And I'm now going to do a null space. I have to subtract 5 off of the main diagonal of A is going to give me -7, -7, -1, -1. Okay, and don't forget that this matrix will never be invertible, right? You will always be able to cross off a row. Here it's pretty obvious. Let's just cross off the top row because it's got messier numbers. And of course, I can set up my free variables and, put it, so here's a pivot, right? You set up your free variable, solve it by back substitution. But I am just going to use, remember that A-B trick that I showed you guys? Where you swap when you have just two numbers in a row in a null space, you can swap the two numbers and just put a minus sign on one of those two numbers. So what I'm going to do is go straight to my vector here. And I'm going to put the minus sign on the second entry and turn it back into a +1. Is that too fast? I mean, basically, this is just x plus y equals 0. So y is equal to t, and so x is equal to -t. So we bust out the t, you get that vector. Okay, so that's what's going on right there. And that's my first eigenspace. Okay, let's go to the other lambda. Lambda equals -3. Again, I have to do a null space. I'm going to add 3 to the main diagonal of the original matrix A. So I add 3, and I get this matrix right here. 1, -7, and then on the second row, -1 and 7. Again, I must be able to cross off a row. Let me just cross off either row, it doesn't matter. And then, I can again solve it by back substitution, or I can use the same trick again and swap the -7 with the 1 and change the sign of either of the two entries, and I'll change the -7 into a +7. So the -7, I'm switching to positive. Make sure that you understand how this trick works. If it's not clear, I hope somebody will jump on me about it, because this is something you want to be able to just do. It's just fast. It saves you the hassle of introducing free variables and writing down an equation and busting out variables. It's just very quick. I taught that. I think we didn't learn that right away. I just taught it in chapter 7 when we got to that point. Okay, so we have a couple of eigenpairs here. Yes, Sebastian.
How come for the first one, for lambda equals 5, the top one is negative, but for lambda equals -3, the -7 becomes positive?
It doesn't matter, actually. So with that A-B trick, when you have this, it's your choice. Do you want to write it like that, or do you want to write it like this? They're both correct, because they're actually just scalar multiples of each other. So it actually makes no difference. If this is correct, then so is this. If this is correct, then so is this. It's kind of like you get to take your pick. Does that make some sense? Yeah. Okay, great. Any other questions so far? By the way, just to get the notation, you might want to come back in your notes here. These are the lambdas. I'm going to call them lambda 1 and lambda 2. And then the vectors here are just the V1 and the V2. So we could label those so that it matches our recap notes over here, right? We've got our subscripts going. So let's go ahead. I'm going to write down my first solution, x1 of t. This is going to be e to the 5t times -1, 1. Go ahead and put a box there. And then the second eigenpair gives me a second solution, which I'm going to call x2 of t. And this one is e to the -3t times 7, 1. Okay, and I'll go ahead and box that one as well. We've got our two solutions. And these guys therefore are the basis. It says it over here, it's the basis solutions. And we can now write the general solution. Let's write down the final answer. In other words, the general solution here it is, x of t. I'm just following along from the recap notes that we see. X of t is C1 times e to the 5t times the vector -1, 1 plus C2 e to the -3t times the vector 7, 1. And that's it. Yes.
So that means you're gonna get two equations for your general solution if you actually multiply it out.
Yeah, let me, well, so there's two, this is a solution and this is a solution.
Yeah, but multiply it, you're gonna get e to the negative e to the 5t and e to the 5t, so you're gonna get two equations.
So we can actually, let me, I was gonna make this remark in a moment, I guess I'll make it right now. We can actually compress this, I'll do it in blue right here. We can compress this into sort of a top slot and a bottom slot. What I mean by that is if we ride along the top of the slots of both terms, then what I actually would have would be what? C1 with a minus sign. So minus C1 e to the 5t, and then plus 7 C2 e to the -3t. So I can do that. And then if I instead ride along the bottom of the vectors, then I have a 1 here times C1 e to the 5t plus C2 e to the -3t. So this is what I would call the compressed form. People will ask me, well, what's the correct answer? Is it the blue part or is it the part that I put in a box over here? And my answer to that is they're both the same. They're both correct. It's just two different ways of writing the exact same thing. So if you want to compress your solution, you'll see this in the back of the book more often just because they don't like to use so much space. I personally prefer it this way because I like to see my basis vectors. I like to see the linear combination. As somebody who loves linear algebra, right? I sort of prefer this because I see that, linear combination of solutions right there in front of me much more clearly. Does this make sense so far? Now, I'm going to make a couple of remarks about this example, and then we're going to study it a little bit more. The first remark I want to make is that the C1 and the C2, those are, of course, our general constants. If we were given initial conditions, well, we've seen this many times, right? If somebody gives us, say, what is x of 0, then we can actually use the initial conditions to find the constants. So if we are given initial conditions, and this could be written somehow in the form of x of 0. So this would just mean literally, so they might give you some numbers here. Let's just say x naught, y naught, some specific values here. If they gave you those values, then we can solve for C1 and C2. See, if you put in 0 for t in this box here, if you put in 0 for t, do you see that the exponentials just go away? And what you're left with is just expressions with C1 and C2. Setting it equal to this, you can solve a little system and come up with those values. And what is that called when you actually plug specific numbers in for C1 and C2? Do you remember what the buzzword is? What kind of solution is that called?
Particular solution.
Exactly, Josh, thank you. It's called the particular solution. So this is called the particular solution. So the general solution is the one that has all of the constants in it. If you solve for those constants, you obtain what is called a particular solution. Okay. I'm gonna actually, in a couple minutes, I'm actually gonna draw a couple. We're gonna look at some. Well, actually, this is a particular solution right here. This is the particular solution where C1 is 1 and C2 is 0. This one is another particular solution where the C1 is 0 and the C2 is 1. Okay. Now, here's the problem, guys. The problem with all of this, the problem with what's on the sideboard, the problem with what we've written down so far is that we can sort of lose sight of what it actually means. It's a little dry, right? Oh, we have the matrix, okay, find the eigenvalue, eigenvector pairs, and then just write this down. You can sort of become very robotic and mechanical about that and just kind of lose track of what's really going on. A great way to bring us back to reality, guys, this is often the case, is to draw pictures. Sometimes I feel like in Math 250B, we don't have, after you just got out of 250A where you were drawing pictures every day, all day, right? You get into this class like, well, where's the pictures? Well, I'm going to give you a picture for this, okay? So what we can do here is we can visualize, this is my second remark, we can visualize the solutions to the linear system by drawing, and we can visualize the solutions to the linear system by drawing what is called a phase portrait. A phase portrait, and I would like to show you the phase portrait right now for this example. So we're going to draw a picture here. This will be drawn in a two-dimensional plane. And actually, coming back to what I wrote over here, if I just read on the top and bottom entries of this vector, both of them are functions of t. And the axes that I have over here, I'm going to label those with those two functions of t. Actually, this gives me a minute to remind you of something from your calculus class. I wonder if you remember. Do you remember somebody says parametric equations? Do you remember learning that? If I have a fly that is buzzing around in this room and tracing out a curve, and I wanted to describe that curve, if I want to describe a curve that moves in 3D, turns out you have to do it parametrically. You can't do some kind of like an mx plus b or anything like that. It doesn't work. You have to describe a curve in 3D parametrically. There's no other way. And so, of course, in calculus, you learn about that. But actually, if you think about it, what I have here, my friends, is literally a set of parametric equations. T is my parameter, and my top slot is a function of t, and my bottom slot is some other function of t, and I can plot points. I can plot points and come up with where the fly is on the surface of my phase portrait. That's what I want to do right now. I would like to draw pictures, right? And I want to draw solutions to my linear system. Remember, guys, there's infinitely many solutions here, right? C1 and C2. So let's do this. Let's draw curve A is going to be C1 equals 1 and C2 equals 0. I'm going to make this really easy. To start with the simplest one I know, which is to choose C1 to be 1 and C2 to be 0, which actually means I'm looking at this. Would you be able to plot this if I asked you to? If I asked you to sketch this on this picture? Question is, could we do that? Well, it's the same thing as plotting parametric equations, right? You plug in a value of t, and then you plot a point over here. What's the easiest value of t that you know? 0. How about 0, right? You plug in 0 for t, e to the 0 is 1, we just get negative 1, 1. Okay, let's plot that. Negative 1, 1 is right there. That's actually kind of my initial condition. At time 0, this is where the object is. Now here's my question. What happens with this solution as time goes forward? So like if t is equal to 1 or 2 or 3, I have this vector that is being what? Stretched by whatever the e to the 5t, that's just a number, right? E to the 5t is just a number. There's a stretch factor. This stretch factor gets larger and larger as time goes on, right? So don't we just take this vector, this is the vector negative 1, 1. Aren't we just going to see as time goes on that this thing is going to go off like that? It stays on that same negative 1, 1 vector direction, but it just gets stretched longer and longer. And actually, you really want to know the truth, it accelerates as time goes on because this exponential function blows up really fast. So if you start your stopwatch at time 0, the solution is right here, and then you let your clock go, that solution is going to float this way, but faster and faster and faster off to infinity. So I like to draw arrows on my curves to emphasize that. The other thing is, of course, you could go in reverse time. You could say, well, what would happen if t went backwards? If t went back towards minus infinity, if this was a VCR tape, you guys even know what those are? I'm old enough to know what they are. Anyway, if you go backwards in time, right, this trajectory would actually go back towards the origin. It would never quite get there, but it would go backwards towards the origin because e to the negative infinity is like going to 0. Okay, so this is one picture. Let's label this with A. That is one solution curve with a particular choice of C1 and C2. Now, another choice, let's do case B, would be to switch this around. Let's let C1 be 0, and let's let C2 be 1. Now, we're talking about this curve, actually. So if C1 is 0, and then C2 is 1, now we're talking about this curve. Again, at time 0, I put in 0 for t, I get the vector 7, 1. So I better plot that. 1, 2, 3, 4, 5, 6, 7, 1 is right about there. And now can somebody tell me, as I start letting my clock go forward from the vector 7, 1, and I'm scaling it by e to the negative 3t, what is going to happen to that vector as time goes forward?
Smaller.
So e to the, as t gets bigger, this is a negative exponential. Negative exponentials go towards 0, right? So actually, exactly what Nathan mentioned, we're going to shrink this vector down. So it stays in the same direction, but it is, this time the arrows need to be pointing towards the origin. Okay, so this would be curve B. Of course, you could go backwards in time and see that this thing was coming in from toward out by infinity somewhere, but that's basically what the way that curve is going to look. A couple more really quick, and then we'll kind of wrap this up. We could also just use the negative of the first solution. So if I put a minus 1 right here, if I put a minus right there, that just puts a negative on the whole solution x1, which basically just means you're going to turn this solution around. Okay, so it's just going to go that direction. This is curve C. This is curve C. And then finally, I'll do the same thing with the B curve. So we could let C1 be 0 and C2 be negative 1. Now we're talking about a curve that's coming in from minus infinity coming towards 0 from the opposite side as curve B. Yeah, Josh.
So we want this to be on the exam or the final, like we're gonna have to like graph it.
I might, yeah, I might do that. It's always a little hard because it's like, well, how many curves are you supposed to draw? I mean, after all, there are infinitely many solutions. So far, I've drawn 4 of them. The question would be like, how many should you draw? Well, I mean, what if my initial condition had me right here, for example, right? There's got to be, like, if that's x of 0 at time 0, where does this solution float as time goes on? The answer is you basically look at the trend of the arrows that you already have and you fill it in a consistent manner. So this would be something like this. Now, to do it perfectly, of course, you would need a software and a computer to draw pictures of these phase portraits. They certainly could do that for you. One thing I will tell you, these curves could never cross each other. They never cross each other, and the arrows have to be kind of in a consistent manner, yes.
So it's kind of similar to like a vector field.
It is, yeah, somebody in my first class mentioned the exact same thing, it's like a vector field, absolutely. Also, we could go down here, we could draw, so these curves would look like this here, I'm just following the direction of the, sort of the general flow of the arrows here. This one's gonna go like this, and like this. This is it. This is a phase portrait. Okay, the way I want you to think about this, my friends, I want you to think about this like this is the surface of the ocean. It's the surface of the ocean, and what these lines and arrows show us are the currents in that fluid, in that water flow. So if I drop a feather, somewhere on the surface of the ocean, what this phase portrait now shows me is how that feather is going to flow, right? We just follow the trajectory of the phase portrait lines, right? So you just have, basically, this is just the swirling ocean, right? And you're imagining just putting a feather right on the surface of it and watching it trace out a path. Does that make sense? Why am I showing this to you? Again, it's so that you have a vision, something to visualize. You can actually have a picture that goes with all this abstract calculation. Right, that's kind of the idea behind it. By the way, this has a name. This is called, this particular phase portrait, this is called a saddle. Oh, do you guys remember the good old hyperbolic paraboloid from your Calc 3? I cannot draw that thing to save my life. That's the thing that looks like a potato chip shape, or it also looks like a horse saddle. And if you draw the level curves, remember this from calculus? You draw the level curves of one of those surfaces. Well, for a hyperbolic paraboloid, they're going to look like this. Okay, so you have probably seen this kind of a graph before, but here we're seeing it in the context of solving a linear system of differential equations. Okay, so let's just test our intuition here a little bit. I'm going to make a couple more, I'm going to come back and make a couple more notes here. Can somebody tell me why this phase portrait looks the way it does with, you've got some lines that are coming towards the origin, some of them are going away from the origin, and we end up with this saddle behavior. Ultimately, at its core, why is that? What feature of the math itself is causing our picture over here to look like a saddle? Any ideas?
Is it the E?
The exponential part. What is it about the exponential part?
It shoots off or decreases at some point, depending on the exponent.
Depending on the exponent. What are the exponents? 5t and negative 3t. Where did those numbers come from? The 5 and the negative 3. Oh my gosh. Oh, those are the lambdas. One of my lambdas was positive, and that gave me the arrows going out. And the other lambda, which was negative 3, that's negative. That's the one that created curves that are coming in. Aha. So let's put that down. If lambda 1 is positive and lambda 2 is negative, then the phase portrait is a saddle. You get this saddle behavior in that case, where one of them is positive and one of them is negative. Yes.
Wait, that applies if it's flipped as well, right? As
Yeah,
long
yeah,
as
yeah.
One is.
One of them is positive and one of them is negative. Yeah, exactly. Okay, great. So now I'm going to challenge you for a minute. let's imagine that both of my lambdas are greater than 0. Okay. So that would mean that my exponentials are positive everywhere, right? So if that happened, then thinking about the picture, all of the arrows would be going out, right? In fact, I could draw a picture maybe before I even write down what it is. I'll draw a little picture. You'd have your phase portrait, right? If both of the lambdas are positive, notice how all of the arrows, every single one of them is going outward. It's just because of these lambdas being both positive. Does anybody know what we might want to call this?
I have peak.
Actually, there'd be lots of words you might think of. It starts with an S as well. This is an example of something that is called a source. So in this case, it's like the sun, right? The sun is the source of rays that go out in all directions from that source. So this is the phase portrait for a linear system where both lambdas are positive. Now, another possible scenario, I bet you guys are going to be a little bit ahead of me on this one. So if we have two lambdas that are both negative, and then we ask, what is the phase portrait? Let me draw a picture. So for this one, of course, what's happening, right? I'll just draw all of the arrows go inward now because every exponential is negative, right? So the t, as t gets bigger, I don't care where you drop your feather in down here. As time goes on, that feather is going to get sucked into the origin. What do you imagine I'm going to call this? It's actually a sink, yeah, but it looks like, oh, we call it a sinkhole. There we go. Yeah, it's basically, it's generally referred to as a sink. So we have saddles, sources, and sinks, and we now have a picture of all three of those phase portraits look like on the board here.
So they all start with an S.
They do. And actually, we're not done with this story either. So there's going to be a little bit more to it. We're only going to talk about phase portraits for a 2x2. If you had a 3x3 problem, then you would need a 3D picture. I mean, it is already hard enough to draw just a 2-dimensional picture. So don't worry about anything more than just a 2x2 for this little bit of the analysis. But just kind of knowing the behavior, the thing I really want to emphasize is that if I ask you on the test, what is the qualitative nature of the phase portrait for such and such a linear system? You have to realize that I'm giving you a gimme. Because all I'm really asking you is, what are the lambdas? Are they positive, both negative, or one of each? And that dictates whether you have a saddle, a source, or a sink. Pretty straightforward. Any questions on any of that? That's so good. You know, there probably are a few questions in your mind right about now. Of course, one question is the looming question. What are we going to do if the matrix is defective? That's going to be a problem, right? So I'm going to push that off a little bit still. Another question that's maybe a little bit more on the front of our minds in this context is simply, what if the lambdas are complex numbers? Because we have seen that. That can happen. You can get lambdas that are imaginary. So we're going to have to go through a whole bit about that. Yeah.
So what if both lambdas are 0?
Okay, I'm going to skip talking about the lambda case of 0. 0 is not part of my notes here, obviously, as you can see. I mean, if the lambdas are 0, then you just don't have the exponential. It means that you have, a particular place where the feather just sits there and never moves. It's not, you can still draw a picture of it, but it doesn't have like a name like these phase portraits here do. So I just chose not to. We're not going to get really hardcore into this. If anybody's out there worried that, oh my God, I hope I can draw these things, I'm not going to be asking for perfection on these kinds of pictures. Just knowing the qualitative behavior is a big part of it. Okay, but that does lead us to a question. What about complex lambdas. And the best way for me to discuss this case, guys, is to do an example. So we're gonna just do an example of this and we will see how to handle it. Do this to finish out the first half of our class today. So let's just write down an example. Suppose I want to do this example right here. Let's solve x prime equals ax, where capital A is going to be, oh, I gotta get the matrix right. Yeah, 9, 29, -1, and -1. Okay. So same thing as the last problem, we would like to find the solution. It is definitely going to be a two-dimensional solution set. That's what my notes say over here. And let's just check it out. Let's do our determinant here. So I have to do the determinant of a minus lambda I. So I'm just going to subtract lambda off of the main diagonal of the matrix. There it is. Subtract the lambda. And as usual, I can just do my little 2x2 determinant formula here. It's going to be something like that. So 9 minus lambda times -1 minus lambda, and then we add 29. And when I multiply this out, I will get lambda squared minus 8 lambda plus 20. So hopefully I did that right. Lambda squared minus 8 lambda plus 20. And as always, we're going to be setting that equal to 0. Okay. I can use the quadratic formula here. This one does not factor nicely. I could just use the quadratic formula. I get 8 plus or minus the square root of 64 minus 80 all over 2. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Have that right? Just my usual high school quadratic formula. And 8 over 2 is 4, right? And then under this radical, I actually have -16. So when you take the square root of -16, what do you have? 4i, which then has to be divided by 2. So we end up actually getting 2i out of that. Okay, so here we go. We have imaginary roots. Now, they are not repeat roots. So I actually, since there's no repeats, I do know that it's non-defective as a matrix. So that's at least good. But I'm going to have to live with these lambdas now. So over here, let's work on the 4 plus 2i. I have a null space. And for this null space, remember that we're just going to subtract lambda off of the main diagonal. So we should get 5 minus 2i, 29, and then -1, and -5 minus 2i. There's my matrix. It's times like these where understanding the theory really helps us out. We have to know that it doesn't look like it, but these two rows have to be multiples of each other. Have to be. Because we're finding an eigenspace right now. So we can cross one of the rows off without having to do any EROs to figure that out. Let's just cross off, in this case, I'll cross off the first row. And then I'm also going to jump ahead and use my AB trick thing. Remember the trick, right? What I'm going to do, I'm going to swap these entries. And I'm going to change the -5 minus 2i to 5 plus 2i. And then I have a -1 below that. Do you see how fast that is? I didn't have to do any EROs. I'm not even breaking a sweat so far, right? By using those little tricks, we can really speed this up and be pretty sure that we didn't make a mistake as well. Okay, so that's something you want to know. Now, one thing we are going to want to do here, I'm going to do it right now. I'm going to split off the part that does not have I on it. Notice that the 5 and the -1 have no I. And then I'm going to put as a separate term over here the I part. So there's a 2i on the top slot and a 0 on the bottom slot. It's kind of like busting out the variables that we did way back when, except here we're busting out an I. It's the same idea.
That sounds violent.
Pardon me?
Busting out an eye, that sounds violent.
Yeah, that does sound bad, doesn't it? Yes, that's exactly right. We're busting out I right here. Okay, so I have an eigenpair right here in front of me now. With me, is everybody so far so good? This is actually, so far, it's all just chapter 7. And we did this a couple weeks ago anyway. So this is good review. Now, I have a little bit of good news here. I know it's not good that we have imaginary numbers, but there is a little bit of good news, which is that we can actually ignore the other lambda. So there is another lambda, of course, which is 4 minus 2i. I just want to point out we can basically ignore it. And the reason is that in a moment, I am going to actually show you how to get 2 solutions just from this lambda. Now, I'm not saying that this lambda is now over pulling its weight or anything like that. I'm just basically going to say that we can extract 2 solutions from this one lambda. It's not that it's producing the 2 alone. It really is a pair of lambdas producing 2 solutions. Yeah, Josh.
Is that like a rule then whenever you have an imaginary lambda, you only need to solve for one?
You only need to solve for one of them, and I actually would recommend solving for this one.
The positive one?
The positive one, yeah, exactly.
Really quick, the null space was a 3x3 matrix. How do you know which rows are multiples of each other? Is it all of them?
That can be, it may not be that any of them are multiples of each other, but you do know that you can cross off a row. As long as the way that you can figure it out, it's a really good question, and you'll watch, if you watch my review session video, you'll see an example of a 3x3 that has imaginary numbers in it. As long, here's the test. Whichever row you cross off, the rows that remain should be Li. So the rows that remain should not be multiples of each other at that point. Now, in this case, there's only one row that remains, so there's no problem, right? But in a 3x3 case, there would be 2 rows that are not crossed off. As long as they are not multiples of each other, then you cross off a good row. Okay, great. Is everybody with me so far? Well, let's try to write down, actually, I need a lot of room for this. Let's write down the solution, and I'll do it over here. Remember, guys, we're going to present this solution to our engineering boss. And our boss probably doesn't want to see an imaginary solution that he can't draw, can't plug into, can't make any physical sense of. Right? So we're going to need to figure out how to get rid of the imaginary numbers, and I have a beautiful way to do it. And here's what we're going to do. We form a solution. I'm actually going to label this x of 1, 2. You'll see in a minute that we're going to get 2 solutions out of this. And here's what it is. We're going to take e to the lambda, here's lambda, times t, and then times v. V is 5 plus 2i and -1. There's my solution. What I put down right here, guys, what I put down right here is simply following, it is simply following this, right? E to the lambda t times v. I literally just wrote that down for this eigenpair right here. The problem is you can't hand this to your boss, because I don't even know how to graph it. I don't even know how to plug it into a calculator. I don't even know what it means. So what I'm going to try to do in the next few steps is get rid of the I. Yes?
Would the e to the I turn into a sine and cosine?
Yes. So one thing we're going to use, let me put that up here. I don't know if you guys remember a few weeks ago, I mentioned this Euler formula. E to the I theta is cosine of theta plus I sine of theta. I'll just remind you over here about that. We will be needing that. Okay, so we have that, and then, so let's just start working on this. There's an e to the 4t. I'm just going to pull that way outside. Okay, and then I have that gets multiplied by e to the, what is it? 2it. 2it, so the 2t is the theta. So this is just cosine of 2t plus I times sine of 2t. Okay. So that's just the Euler formula. And for the theta is just 2t. You see the 2t right here. Okay. And then this vector, I'm going to use the split up version right now. So I'm going to write this as 5, 1. I'm sorry, 5, -1 plus I times 2, 0. Okay, gotta keep this straight. Okay, now the e to the 4t, that part doesn't bother me, that's kind of on the outside. But what's inside the big braces is just something plus something times something plus something. If I ever came across something plus something times something plus something, here's really what I have. I have A plus B times C plus D. What would you normally do with this if somebody asked you to simplify it? Foil it out, right? You would foil it out. It's exactly what we're going to do, except we're not going to do foil. We are going to do Floyd. Floyd, we are going to, what the heck am I talking about? We are going to foil it out, but not in the standard order of first, outers, inners, and last. We're going to start with the first. The first would be what? Cosine of 2t times 5, -1. Okay, that's the first term. Now, why am I going to jump to the last? Now, the last would be BD, right? The BD part. Why do I want to jump to the last here? I have, this is this part times this part. What's so nice about that?
I times I.
I times I. Anybody want to remind me what is I squared equal to?
-1.
-1. We get rid of the I that way, right? We get rid of the I. So we have I times I. So -1 times the sine of 2t times the vector 2, 0. So all of that, okay, let's just label this as the F and the L part, right? The first and the last. And we're putting that together. And so far, at least, I don't have any I in my answer. Now, when I go to do the outers and inners, you'll notice that both the outers and inners do have an I on them. We have to live with that. That's just the reality of it. There is an I there. And the outer term is going to be cosine of 2t times 2, 0 plus sine of 2t times 5, -1. This is just outers and inners. So there is your Floyd, which you will want to know how to do. So far, so good? Remember, the whole goal is to get rid of I. Oh, we've almost done it. There's only one place left where there's an I, and it's just right here. Everything else on this line, there's no more I to think about. But here's what we're going to do. We are going to just take just this first part as a solution. Okay, so we extract, actually, we're going to extract 2 real solutions. Let me write them down. The first one is x1 of t, and that's just this first part, e to the 4t times cosine of 2t times 5, -1 minus the sine of 2t times 2, 0. Okay, so we're going to just take just that part. There's no I there. There's no I there. That makes me feel a little bit better about it. And we're going to extract a second solution. And the way that we're going to get the second solution, guys, we got to keep the e to the 4t. I'm going to recopy that because that's outside of everything. We have e to the 4t out here, and we're going to multiply that, my friends, by the rest of the outer and inner term, but without the I. Without the I. So this is cosine of 2t times 2, 0 plus sine of 2t times 5, -1. This is my second solution. Now, some of you are probably sitting there thinking, well, why can you do that? Here's the solution. Why are you allowed to chop it into 2 and just keep this half and this half, right? I'm not going to show you guys all of that detail right now. Suffice it to say that if we went back and actually looked at this other lambda and worked out a whole nother sort of messy solution like this that goes with this other lambda, we would be able to combine that solution with this one. Remember, the solutions are closed under addition, subtraction, scalar multiplication, all that good stuff, right? We would be able to make a linear combination that would get this whole part to cancel out and just leave us with this. And then we would be able to do another fancy linear combination to get this part to cancel out and leave us just with this. And that's how it works. That's how it's actually done. We don't need to see all of that detail. It's way too tedious to write it all down right now. But suffice it to say that we can get away with extracting these 2 solutions. Folks understand this all right, Sebastian?
Are we just switching the, I think the G's, like the 5 and -1 and the 2 and 0?
Yeah, a little bit. Okay, so I want to make a comment about, thank you, you reminded me of something I wanted to say. There are some students, I've noticed the many times I've taught the class, there are some students who like to sort of memorize where things go. It's like, oh, there's going to be a cosine and a sine, and one of them has a minus sign, one of them has a plus sign, and the vectors get mixed and matched or whatever. I don't think it's worth it. You got enough to memorize in your life, right? It's probably better to just be able to derive this thing, right? Just be able to do the Freud, then you don't have to worry about memorizing what goes where. But you're absolutely right. It's kind of it is something you could write down a particular recipe for if you wanted to. Okay. I'm going to leave you with this teaser where we're going to go take a 10-minute break. During the 10-minute break, if you are really into this, I'm going to ask you a question to think about, and then we'll answer it in 10 minutes, which is, what would be the phase portrait for these solutions, right? So we're going to have to think about that. There's sines and cosines now. It looks a lot messier. But in a few minutes, in 10 minutes, I will come back and tell you, no, I don't want to hear now. I will come back in a few minutes and we'll talk about what the phase portrait for the system looks like. Okay? So let's take a break until about 3:13. Okay, I'll give you 10 minutes to decompress a little bit and then we'll continue. I'm trying my best. I know. It's probably the weather or something. I think I noticed in my other class, a lot of people are tired too. Yep, I get that. Coming up. I only have 3 lectures left after today. Actually, I only have 2 lectures left after today because we have a test next Monday. Wow. You guys can start counting down. How many more hours do I have to listen to Dr. Ann? Oh boy. It's pretty crazy.
And then she wrote all this stuff all over.
Yeah, so I didn't even work for like 36 hours. Like Friday, Saturday, Sunday, just 4-hour shifts every day. Bowling job, so let's see who can do it. It's I gave about a year in Los Angeles. I did. Is medium medium, we get corn and potatoes, or is corn, potato, eggs, sausage, what? Or just yeah, you get sausage. Sausage is such a pain. Yeah, because you gotta cut it individually. There's some freaks in nature that order like 6 at a time, like 6 sausages individually. I mean, I can do 3 at a time, but it's just such a hassle. It's 12 hours. I can't do anything. I wake up at 9, going at 11, and I come back until like 6. And then we have 6 hours.
It's like our algorithm is perfect. It's just. No,
I have my dog fall asleep.
I kind of get like 96.
I literally. No, he didn't. Yeah.
I know, I was kind of surprised. I didn't think it was gonna first one. It was kind of annoying because we're supposed to make we didn't actually write a paper, like we're supposed to make a poster. But we had this, like you have to try and fit everything on like one sheet of paper. We have so much stuff to write. So it's kind of hard. And she wrote stuff and she's like, oh, I have more diagrams and stuff. I was like, well, I'm already out of room. Yeah.
Did you get X too? How do you get X? Or you don't know? OI. Just. Oh.
Middle of the road.
I thought it was like, I don't know why, I didn't see it.
Oh.
When I see photo, I feel like
If you take 375.
it's fine.
That's all.
What the?
But if I hadn't taken that class, it would be kind of hard.
First thing
You know, it was like a mid class. Dr. P. Dr. P's amazing. I had him, I got one doing twice. I had him for 131, then I had for 375. Dave Stratton.
Oh.
I got lucky.
That's 300.
No, the 100 one. But the thing, professors, they don't listen.
Yeah, let's say that was.
Also, at the end, she said, put references and citations, but on my own citation, they do the whole thing, so. Like, what do you put, you just cite yourself? I mean, I can cite my data set, I can cite like Python. Python only has 3 points of the. I didn't read it, I took 2 classes this last week. And I. So I don't even wait because there's just no content for it. It's
You go to the
like,
office? Oh, yeah.
yeah, it's just like nothing.
And then we got another class.
I'm just trying to make it on coding class.
Oh, okay, okay, there's gonna be more of that month. then.
Yeah.
Good, good. Busy with that this weekend, huh?
And then for the lecture, it was just 2 examples.
The entire class is just opinion. anyway.
Yeah, I've just done the 2 examples, but I've been, of course, filling in a lot of.
Yeah,
what
you
need to know.
are.
Yeah.
I'll just rewatch your lecture.
Yeah, if you missed the beginning, that's right.
You're supposed to be able to make your opinion. Did you do anything this weekend? I was writing class next semester. I've never had a Saturday class. Actually, I'm taking something over the summer, so I don't have that Friday class. I have my last class on Thursday is this machine learning class, and it's one of those 3-hour classes, and it's at 9:45. it's just one side.
I used to teach those.
Yeah, that's the cost.
And I still notice the cars streaming out of the campus at like 9:55 every night.
Yeah.
Yeah, he must be home by this time. Yet there's more traffic lined up on Nutwood Avenue at 9:55 at night than most of the rest of the day, because everybody was on campus getting ready to leave. So I try not to leave at that time.
It's just too long. 3 hours is so long for a class too.
Even 2 hours.
Yeah.
Can be a lot, yeah. No doubt about it. Good. Great. That's right. That's what I was teaching remotely. I could still come in here and I could just write like this and I could just like scoot around. I would never have to stand up. I could live with that.
Yeah, I know you do this. I remember that. It's about Eugene. I'll start it next week. I was like so ready to go in tomorrow. But I have to get like a physical check. For like the yeah. Yeah. Check. No, this is like not this. That's 2 hours, which is slow. Yeah. It has your number. It's like literally chicken curry.
So we're gonna teach, especially like show us all the process. Yeah.
All right, everybody, I think I'll go ahead and kind of try to get everybody's attention here again for a quick minute. You know, on that last example we did right before the break, I forgot to close the loop and finish the total final thing. The general solution, just to fill in one last thing, I recopied it here during the break. The general solution is just linear combination of the two basis solutions that are down on the bottom. So up at the top, you notice I just have C1 times the first solution plus C2 times the second solution. And as always, if somebody gave you the initial values, some initial conditions, then you could actually even solve for C1 and C2 as well. So that's just the last step I forgot to explain earlier. Anybody have any questions about how this FLOY thing works? It's really just foiling out an expression, but just doing it in a different order to kind of gather up the real and imaginary parts separately. Does that make sense? That's how we extract these two real solutions here. Okay, one other thing, before I started classes, I forgot I had one other announcement I wanted to make. I sent you an email about it this morning. You are going to get pestered for the next 2 weeks by the administration or somebody who controls the portals to fill out your SOQs for all of your classes. And I would like to really encourage you that I would really appreciate you filling out a form. Just take a few minutes and fill out an SOQ about the class. You might be sitting there thinking, oh, well, he's taught this class a million times. He doesn't need any other advice or whatever. Actually, I would love to get your advice, things that you liked, things that you didn't like. In part because I'm actually relatively new to, recording my lectures in Zoom and having office hours kind of with Zoom and in person. I didn't even use Canvas or Titanium prior to the pandemic. That's all been new for me. So the stuff with the online resources, I just would really like to know what you guys have thought about everything. So if you have feedback for me, take a few minutes, just fill out comments and send those SOQ forms in. I do read your forms and take them very seriously right before I do the final grades. No, just kidding. No, I read those. They can be totally anonymous. I read them like next year sometime. I'll get a chance to take a look at that. So, but yeah, I would definitely appreciate that. Okay, what I would like to do is come back to that question that I tried to tease you with before we took our break, which is I want to talk about the phase portrait for a linear system that has complex lambdas. So over here, right, you'll remember that we've already got a few scenarios outlined. If we have positive and negative lambdas, we get a saddle. 2 positive lambdas gives us a source. 2 negative lambdas gives us a sink. But I want to talk about what would happen with these imaginary lambdas. I'll give myself some room here. So let's just look at this first solution here. Right, this would be if I took C1 to be 0 and I took C2 to be if I took C1 to be 1 and I took C2 to be 0, this would be my solution. I would like to think about how we would draw this solution. Okay. Let's imagine for a minute that the exponential is not there. And I'm just looking at this thing right here. Do you see that this is just a bunch of sines and cosines with attached vectors that are just constant vectors? Would you agree that, sine and cosine, they repeat themselves every, 2 pi units? So would you agree that if I just start forgetting about the E part, right? If I just look at this part right here, would you agree that as time goes on, whatever this object is doing is kind of going in a circle and coming back to the same point every 2 pi units? Yeah, in fact, if I was going to draw a picture of it, if I drew a picture of it, I'd have maybe I drop my feather into the ocean right here. And after another 2 pi units goes by, it's going to just come back to that same spot again. But what does the e to the 4t do to it? It's like the radius. The e to the 4t is kind of like a radius. It's a stretch factor. This is some scalar that is getting bigger with time that's stretching out whatever this vector is. So would you agree that the feather doesn't actually end right back up here again, but ends up out here somewhere? And to get there, all the while, as time is going on, that radius is getting larger, right? It's going to do something like that. And if I keep going, it's going to just keep doing that. I'm running out of room, right? Or maybe I should go backwards in time. So what is this?
A spiral.
This is a spiral. It is a spiral behavior, and with the arrows indicating that it is going outward, right? So in this case, I'm gonna come back and make a few more notes here, guys. I'll make a few more notes. I'll do another bullet point. If lambda is a plus or minus bi with a greater than 0, so why is it an outward spiral? It's because of the 4t here, right? The e to the plus 4, that's positive. The a value, right? This is a right here, the a and the b. The a is 4. Because that a is 4, that's what's stretching it bigger and bigger and bigger with time, yeah? So in this case, we get what is called an outward spiral. There's another name for it. It's also called an unstable spiral. So either word is okay with me. It's an unstable spiral. Its arrows are going to go outward. That makes some sense? The outward nature of it is because the exponential function is swelling the vector itself. It's stretching it out longer. So that if I drop a feather somewhere here, it's gonna go in this circular spiral orientation, and it's getting farther from the origin because as t gets bigger, this e to the 4t stretches that vector way up, right? Remember, there's really a vector here, right? You have a vector, it's just a vector that points to somewhere on this curve, right? You have all these vectors. At every value of time, there's a vector here. Right. Okay, great. Well, anybody have an idea what would happen if the a was less than 0? If we had like a -4 or negative number here out in front, then what would happen with this vector function being affected by, say, e to the negative something? It would do what? It goes inward, exactly. The spiral would be spiraling inward. You drop the feather into the phase portrait, it's just going to go in a spiral towards the origin. Exactly. So this one is called, there's a little more room here. This is called an inward spiral. Or we could call it a stable spiral. Again, both words are used. Probably the more technical term would be stable or unstable, but then the word that makes more sense as to what's going on is inward or outward. Yes, go ahead, Nathan.
So which way does the vector actually point? Tangent to the spiral or outside from the center?
I've been drawing the position vector. So the position vector, you're talking about these vectors that I'm drawing here.
Yeah.
So all I'm saying is, okay, so as this feather goes around, there's really a vector that's following it. The base of the vector is right here at the origin, right? It just stays there and just follows around. Yeah, it's not a tangent vector, like you had a vector like this, that goes back to another class. That's the velocity vector at that point. And I don't want to get into the velocity
So what
vector.
are the arrows pointing on the spiral?
Well, the arrows that I've drawn on the spiral are just showing you the direction of the motion of this thing. Now, some of you might be wondering, well, how do you know if it's going clockwise or counter? So it could be here's outward clockwise, counterclockwise, but how do you know it's not going the other way? And the answer is that takes a whole lot more analysis than I want to get into here. In fact, they'll do much more with that in some of the 300 level differential equations classes. For our purposes, I just want a rough idea. Okay, so as long as you know that we have a spiral and whether it's going stable or unstable, in other words, inward or outward, that's all I really care about. Okay, there is one more case. Let me see if I can squeeze it right down here. The last case would be, what if lambda is a plus or minus bi, but the a is actually equal to 0. Yeah, this one is just a circle, because in this case, there is no, if you didn't have the exponential part at all, if you don't have the e to the 4t there, then you're just looking only at this part. And this thing really does sort of just trace on top of itself. Every 2 pi units of time, sine and cosine just keep going back to where they were before. So you just literally have a circle. So this one, I want to draw a picture of it, is literally just a circle. And again, whether it's clockwise or counterclockwise, what the radius of the circle is, all of those features are details beyond what I want to get into here. Just want you guys to be exposed to this, familiar with it, just a little bit. Yes.
Could it be just some sort of closed loop, or is it for sure a circle?
It could be skewed a little bit. That is possible. Again, that's a detail that we would have to investigate further. Yeah. Nathan?
Are spirals just basically more specific forms of sources and sinks then?
No, I don't really think of them as being the same qualitative behavior at all. They're really quite different because the sources and sinks have a lot of straight line. The directions of those solution curves don't really change very much. Yeah, these are 6 different outcomes. So if I give you a 2 by 2 linear system and I ask you, what's the qualitative nature of the phase portrait? You got 6 choices. But the nice thing to remember is that deciding which of the 6 choices is correct only depends on the lambdas. It doesn't depend on, going through the foiling out or writing out the solutions or the eigenvectors. None of that comes into play. Just pretty easy, actually. It's just a matter of learning it. Any other questions here on this? Yeah, Sebastian?
Could there be a spiral within a source?
No. No, you cannot, these pictures, so one thing about the solution curves is that they cannot cross each other. So you cannot, there's something about uniqueness of solutions to initial value problems, which goes into, again, a higher level math course, which would basically say that you can never have, any 2 solutions crossing. So if I have a spiral, so here's a spiral, that's a solution potentially, right? Let's just say that that's a solution, right? Then I can't have lines cutting across the parts of that spiral. What I could have is, I could have, this would be a different initial condition, but notice that this blue spiral is not crossing the black spiral that I wrote in the first place at all. So the curves cannot cross each other. That's what I'm trying to say. Nathan?
Does the phasor diagram act as like a bunch of asymptotes for like a bunch of general solutions, or?
I don't think, we'd have to talk about that later. I don't quite understand that question, but yeah, that's something we could get into a little bit more later on, I think. Okay. Any other questions so far? Okay, I'd like to move on. We need to get started anyway on addressing what are we going to do about all of this if the matrix is defective. Okay, and that is the next section. We will not have time to finish this today, but I am going to start it so that you can hopefully get started on this sooner rather than later. And this is basically just the case A is defective. So suppose that our matrix is defective. Now I'm going to give you a little bit of good news before I even get into this, which is I'm going to say that this will be for 2 by 2 or 3 by 3 systems only. That what I mean is I'm only going to cover it for 2 by 2 and 3 by 3 systems. It's not that you can't have a bigger system that's defective, but we are only going to cover this. And I don't know if you realize that there's actually something good about that in terms of making your life easier, which is that means that in this section, there can be no complex numbers. Why? Because if a matrix is going to be defective, the lambdas have to repeat. So if you're telling me I have A plus BI and A minus BI, remember, they always come as a pair. If they're gonna repeat, then that means you'd have to have A plus BI again and A minus BI again. And how many different lambdas, or how many total lambdas do I have here now? I have 4, which means the matrix would have to have been 4 by 4 or larger, right? So this actually implies in this section, we will have no complex numbers, which is just going to make things a little bit easier. This is actually a fairly difficult section, just to give you a heads up, warn you a little bit. It's a little bit of a challenging section. But one thing about it that at least we won't have to worry about are complex numbers. Let's set up an example that we can start talking about this material with. Okay, so let's suppose we want to solve x prime equals ax. And let me write down the matrix A. It's again, I'm just going to do, so today I'm sticking to 2 by 2 examples. On Wednesday, we will spend a lot of time doing some 3 by 3 examples. But today we're going to stick with 2 by 2 examples. So if I start trying to solve this, let's just see if we can start solving it for a moment. I'm going to find my lambdas first, right? So the determinant of the matrix that I get, I'm going to subtract lambda off of the main diagonal of that determinant. Okay, and so when I do that, I'm just going to get negative lambda times 4 minus lambda, and then I tack on a plus 4 at the end of that. And this comes out to lambda squared minus 4 lambda plus 4. And if we factor that, it actually factors very nicely. It is just lambda minus 2 quantity squared. So my lambda is 2 or 2. Those are my lambdas. And of course, we can use the fun facts to check that. Make sure that that's correct. Does the fact that the lambda repeats, does that already mean that the matrix is defective?
No.
Not yet, right? We still have a chance. I mean, maybe this eigenvalue pulls its weight. That's really the question. Does this pull its weight? So we have to check that, right? In this case, there is some question about it. So let's take a look at this lambda. Lambda equals 2, and we're going to do a null space right here. So I subtract 2 from the main diagonal of my original matrix A and write down that matrix right there. And I can see right away that the two rows are multiples of each other. And so I'm just going to go ahead and cross off the first row. I'm also going to just really make my life easy. I'm just going to divide through by 2. So that becomes a 1 and a 1 right there and there. Okay, so just simplify this down. Of course, we have our pivot right here if we want to think of it that way. And at this point, we can very quickly get our vector, which is just, I'm just going to use the A-B trick again to get my vector -1, 1. And now do we know if it's defective? Yes, it is defective because we only have one eigenvector, even though the multiplicity over here was 2. It showed up twice and only gave me one vector. So, I mean, here's where we're at, guys. We have only one solution. x1 of t, we can write this down. It's just going to be e to the 2t times the vector -1, 1. Sebastian, what's up?
If there's a multiplicity of 2 over there for the lambda, is it possible for it to pull its weight since it's a 2 by 2 matrix?
Good. It definitely could. That's why we actually have to we have to actually do the null space and work it out. In this case, it does not pull its weight. I mean, what if this matrix was all zeros? Then you'd have 2 free variables and you'd get two vectors there. Okay, so it is possible. Remember, when the eigenvalues repeat, they might pull their weight, and we have to check it. It always has to be checked in that case. Okay, so we have one solution, but unfortunately, guys, we need 2. This is a 2-dimensional. This is supposed to be a 2-dimensional vector space. That means I need 2 basis vectors. So the question becomes, how do we get x2 of t? how do we get the second solution? And so I want to steer you away from one false approach. When we were in chapter 8 and we saw repeated roots to an auxiliary equation somewhere, if we saw the same root a couple times, you might remember that what we did there was we stacked x's. We would stack x's. So I can't tell you how many exams I've graded where for the second solution, people write this down and they put an x there, right, as the second solution. And first of all, it shouldn't be an x, right, because we're not using x here, it should be a t. And even if you just put a t there, this is still going to be a scalar multiple of the original x1. Okay, it's just not that simple in chapter 9. All right, so in this chapter, to get the x2 of t, we're going to have to work a little harder. But you might remember a strategy that we have used many, many other times in this class, which is when we don't know anything else to do to come up with another solution, what we do is who said it? We guess the answer. That's exactly right. We take a guess. Somebody way smarter and way before me came along and figured out what we should guess to get the second solution. So we will guess the form, and here it is, x2 of t equals, okay, so you will want to know this, e to the lambda times t. That makes sense. That's our exponential piece. And then what we're going to do here, guys, is we're going to do, and by the way, this is not in the book. Most of the rest of what we're going to do today is not in the book. We're going to write W1 plus t times W2. Let's go ahead and put a box on that. Right, and this is going to be where W1 and W2 are to be determined. And I'm going to show you the derivation of those in just a second. So this turns out to be the winning format for our second solution. Okay, this is how we're going to get our x2. We have to figure out what is the right W1 and W2 to make a second solution. Once we've got the second solution, bingo, we have our basis and we can write down the general solution just like we've got on the board over there. Okay, so this is the new material. This is the new part right here. Coming up with this x2. x1 is pretty standard, pretty straightforward, but we need to figure out the x2. So whenever we make a guess, and again, I'm not trying to tell you how I came up with this because I didn't come up with it. But anytime we have a guess that we're going to try and use, what do we usually do with that guess to sort of check it out?
Plug stuff in.
Plug it in. Exactly. We plug it into our differential equation, which in this case is that guy right there. So let's do that. Let's do that. Let's plug that in. I'm going to come back over here and we're going to plug it in. This is exactly what we need to do. It's going to work great. But what I'm going to write down now, guys, is not in the book. And that's because I got a little bit smarter about how to maybe try to teach this than since when I wrote the book. So I hope that you'll like this. Basically, what I'm going to do is I'm going to plug this box into here. On the left side, I have to take the derivative of this. Do you guys see that the derivative requires the product rule? I have something with t right here, and I have something with t over here. These are like two things multiplied together. And so I'm going to plug this guess. Let's do it right here. I'm going to plug x2 into the linear system. This is the system of the day right here. X prime equals ax. So on the left side, I'm going to go with the product rule. First term is e to the lambda t. The derivative of the second part is just W2. Be sure to put arrows on those vectors, guys, just to keep that straight. And then plus the derivative of the first term, which would be lambda e to the lambda t, times the second term, which is W1 plus t times W2. So that's the derivative. So in case anybody's wondering, this is just coming from the product rule. What we did right there is just simply the product rule. On the right-hand side, I just have A times X itself, which is e to the lambda t times W1 plus t times W2. Okay. Now, we're gonna, if anybody's losing track of what we're trying to do right now, let me just remind you, we're on a mission to find W1 and W2. This is the key step. What I hope that you've noticed already, looking at this, is that every single term has an e to the lambda t in it. You see that? E to the lambda t right here, and over here. So let's cancel them. Cancel that guy, cancel that one, and cancel that one. Okay. Now, I still have a t here and here. So some terms have t's and some don't. I'm going to kind of organize them a little bit. So here's W2 by itself now. And then there's plus lambda times W1 right here. And then finally there's t times lambda W2. We have that. Okay. And then on the other side of the equation, I have a W1. And then I also have a t multiplied by a W2. So I'm just organizing my terms a little bit, and that's the best way, I think, to do that. So guys, on the left side and on the right side, things have to match up. For example, the stuff that's multiplied by t on the left side has to agree with the stuff that's multiplied by t on the right side. That would be AW2 matching up with lambda W2. Let's write that down. The t terms, I'm going to do this in blue. The t terms are AW2 equals lambda W2. Now, does that look familiar, by the way? A times a vector equals lambda times a vector. Nathan?
Eigenvector.
It's this eigenvector relationship. It's actually the most important
Eigenpair.
equation in chapter 7. AV equals lambda V. Remember that? Well, here we have AW2 equals lambda W2. What this means, my friends, is that W2 is an eigenvector. That's what that actually means. AW2 equals lambda W2. Okay. I'm actually going to rewrite this as well in another manner. I'm going to subtract everything to the left side. You'll see why I'm doing this in a minute. I'm going to subtract everything to the left side. And when I do that, I'm going to get A minus lambda I times W2 equal to 0. So let's just keep this equation in mind as well. We've done this in chapter 7. We're just rewriting it now here in chapter 9. So in blue, what's going on here, guys, is I'm just matching up. This is the t right here, and here's the t on this side. We're matching them up. We're saying this would have to match up with this. And that gives me all of this stuff in blue. Look okay? Seem okay? Okay, great. Now what about the rest of it? What is, well, I'll just call this the rest. Let's look at what we have not looked at yet. Well, on the left side, I've got, let me put a box around this. I've got W2 plus lambda times W1. And then I'll put a box on the right side around the AW1. And I am going to very similarly do some subtraction on that. And I'm going to subtract A minus lambda I. So just check me on this. I'm rearranging the equation. A minus lambda I multiplied by W1 that should actually equal W2. If I solve for W2 right here, if I solve this for W2, that means I'm going to subtract the lambda W1 to the other side, which is what I put right here. You guys with me? Okay. What's my goal through all of this? We're trying to figure out W1 and W2. This is what we got to learn how to do, okay? So it turns out that I taught this class for many years, just kind of fumbling around with these equations, making my students remember where does the W1 go and where does the W2 go and how are they related? And it was kind of hard to do that. So I found a much better way. And it's not in the book, and we're going to draw it right now. It's a little diagram. This diagram is our ticket to success, I have a feeling. So if I can get rid of all this, this has been up here forever. Rid of this part. Okay, so here is the diagram. This is not in the book, but I think you will like this. I'm going to draw a diagram to help me figure out the W1 and the W2. And the way the diagram works is we put W1 right here at the start. And I'm going to draw an arc. And every time I draw an arc on this diagram, what it means is multiply by A minus lambda I. Okay, so this is a helpful diagram, I think. So if I start with W1 and I multiply by A minus lambda I, checking out the equation that we have, when I start with W1 and I multiply by A minus lambda I end up at what?
W2.
W2. So let's write W2 there. Now, if I take W2 and I again multiply by an A minus lambda I again, then we see from the first equation in blue over here that A minus lambda I times W2 should actually end up becoming 0. So I have a procedure for you. We are going to choose W1. We are going to choose W1 so that it obeys this diagram. Now, I do want to point out that W2 should not yet be 0. We don't want to choose. Actually, we said here that W2 is going to be an eigenvector, which means it shouldn't be 0. So we need to choose a W1 that will survive A minus lambda I, but not survive. So when I do 2 arcs, I go across 2 of these, it means I squared the matrix. It's like I did it twice. So in other words, what we're saying here is that A minus lambda I squared of W1 needs to be 0. Okay. So we're choosing W1 so that it does not survive this matrix, even though it does survive the original. Let's go back to our example, and we've got 2 minutes left. I'm just going to finish this example, and then we'll talk much more and do more examples on Wednesday. So back to our example, the A minus 2I squared. So this is A minus lambda I. So what is A minus lambda I? It's actually, so we take the original matrix A and we subtract 2 from the main diagonal. We did this already, right? We're going to square that matrix. Now, when you square this matrix, you're just multiplying this thing by itself, right? So there's the same matrix times itself. I hope everybody remembers how to do matrix multiplication. It's been a while. So we just do the dot products, right? So just go across the rows. So we go rows of this matrix and columns of this matrix here. Right. So if I do that, I'm going to get, actually, if you work this out, since I'm running short on time, I'm just going to shortcut that to the end. You're going to get all zeros there. Now, somebody's always going to ask me, will that always happen? For a 2x2 defective system, it will. On Wednesday, however, we're going to see that for 3x3 examples, that does not always happen. Sure. Okay, does that make sense? Actually, guys, this is good news because we're trying to choose W1 so that it gets killed by the square of our matrix. Well, what vectors get killed by this matrix? everything, right? This matrix will kill everything. So you can kind of choose W1 to be whatever you want, because whatever you choose, by the way, guys, there's lots of right answers here. We got 30 people in the room. We can have 30 different answers here. Anything we choose pretty much is going to work. Let's just pick anything at random. Normally I would pick 1, 0 or 0, 1, but I'm just going to show you that you can pick anything you want. I'm making this up, right? Every one of you could have picked something different. If I do that, then what is W2? W2 we do not get to choose. W2 comes from this, well, comes from this picture here, right? W2 is A minus lambda I. So let me just do this really quick. I know I'm just about out of time. But I'm going to take A minus lambda I and multiply it by 5, 3. If we do this, and again, I'm just doing matrix multiplication here, you will get what? Negative 10 minus 6, that's negative 16. And then 5 times 2 is 10 plus 6, 16. That looks interesting. The original eigenvector, the one eigenvector that we came up with originally was this one. Look what we've come up with for W2.
Scalar.
It's a scalar multiple of this one. And it does say right here, doesn't it? That the W2 should end up being an eigenvector. Now we see that it is. It's actually just a scalar multiple of the original eigenvector. So it is also an eigenvector. And so we get our second solution. I was also trying to say, guys, is that that won't always happen. Okay, so my final answer here, e to the 2t times W1, which is 5, 3, plus t times W2, which is negative 16, 16. That's my second solution. So I'm fitting that into this format right here. W1 plus t times W2. Last comment for the day, guys. Some students will ask me, can I just change this? Can I just change the negative 16, 16 back to negative 1, 1 again? Is that legal to do that? The answer is absolutely not. You must live with W2. You get to choose W1, but you must then live with whatever W2 turns out to be. You can't massage it later on a whim. Okay, so you have to actually leave the second vector as it's found. So there's your second solution. Make sense, guys? It'll take a little time to digest. This was a lot of stuff today. I appreciate you being patient with me. We are almost done with the material. So on Wednesday, we'll practice this a bit more. And don't forget, I have office hours tonight. If anybody's got questions on the homework, feel free to stop on by. All right, that's it for today, gang. Have a wonderful rest of your Monday. And I'll see you again soon. Bye, Barca.